I want to start with the question, how is math logic? A lot of times people will say, well, math, I love math because it's so logical. A lot of times what they're meaning is it makes sense. But there's also this idea that logic is this unbreakable, this really powerful, perfect thing. And if you can do math, you can do logic, and therefore your reasoning powers are unbreakable. But I want to go ahead and just draw attention to how exactly is math logic. A lot of times the first thing that you learn is counting. You start with zeros and 1, 2, 3, 4, and so on. The difference between 0 and 1 is very stark. It's very easy to see that there is a difference, absolutely, between 0 and 1. But as soon as you're able to make one difference, you can then begin to distinguish other things, because 2 is different from 1 or 0. 2 is actually made up of 2 of these 1s. 3 is as different from 2 as 2 is from 1, which is as different as 1 is from 0. So the same principle is being applied, that 0 differs from 1. And that goes back to the idea of zeros and 1s being your false and true and false values, which is exactly the foundation of logic. That is the fundamental principle of logic. It's the law of identity, that either a statement is true or it is false. Because once you have, let's say there are 5 different items here. There's our 5 different items. I can determine that this one here is different from all others. Automatically, I've just separated it into a category of being this thing, which is, I'll call it 1, and nothing else, which I'll call 0. Then I can distinguish that this in here, part of my 0 category, is actually different than the rest of the 0 category. So I need to have a way to show that it is different than the rest, but it's also not this one, right? This 1. So to do that, I could say, well, I'm going to call it 1, 0. So you can probably see where I'm going with this. This one here, I would then say, well, I want to distinguish it from all the others, so I'll call it 1, 1. So I started out with 0, 1, 1, 0, 1, 1. The next step is to call this one and this one consecutively 1, 0, 0, and then 1, 0, 1. Right? And this is just counting in binary. It's the same idea as 0, 1, 2, 3, 4, 5. Right? And if you were to continue it on. But notice we're using the symbols here. So that ability to distinguish between each one, it just breaks down to a bunch of 1s and 0s. But those 1s and 0s that is our basis for logic. It's trues and falses. Instead of using the symbols 0 and 1, I could have used F and T for false and true. So that's one way that math is logic. Here's another way that math is logic. Let's say you've learned counting, you've learned addition, you've learned to undo addition, so subtraction, you've learned to multiply, which is just doing fast addition, and you've learned to undo that fast addition, which is just fast subtraction, which is division. And then from there, you're able to predict answers to certain potential problems that might come up. And that's why math is really helpful in analysis, in trends, statistics, finding out what will be the answer. You're making a prediction. So here, I have 3 multiplied by something plus 1 ends up equaling 7. Now, you could just guess the answer here. And guessing the answer would be an inductive process. You could guess the answer. You could just, if I plug in 1, well, 3 plus 1 is 4. It doesn't work. If I plug in 2, aha, 6 plus 1, that is 7. So you could guess by trial and error, and that's inductive reasoning, because you're sampling. You're taking more data, funneling it down into one final answer, one conclusion. But you could also use logic and the rules of doing algebra on something like this. Those rules are deductive. That means that they are based on logic, on either true or false values. That also then means that if I have, let's say, 3x plus 1 equals 7. So that means that 3x plus 1 is the same thing as 7. So logically, if these two things happen to be the same thing, then if I take the same thing and I get rid of 1, it's the same idea as taking the same thing, getting rid of 1. Why? Because these are the same thing. So I'm listing out my reasoning here. Because they are the same thing, I can then do the same thing to them and still get an equivalent, which in algebra would just be an equal sign, but an equivalent statement. So from here, that means that 3x has to equal 6. So that just means that 3x is the same thing as 6. Why? So again, to use logic and list our reasoning, why is 3x the same thing as 6? It is because if I had originally known, if I had taken it for fact that it was absolutely true that 3x plus 1 is the same as 7, then by getting rid of the 1, I can do that to the same things, right? Do the same thing to the same thing, and I get 6 over here on the right and 3x over here on the left. So these are now, this is true if this up here was also true, that these two things were the same thing. And if that's true, then this must be true. And if this is true, then that means 3 times something has to equal 6. It has to be the same when I multiply it by 3. So if I divide by 3 on both sides, then that means if I know for a fact 3x is the same as 6. So if I take 3x and I divide it by 3, that has to be the same thing as taking 6 and dividing it by 3. When I take 6 and divide it by 3, I get 2. When I take 3x and divide it by 3, I just get x, 1x, because 3 divided by 3 is 1. So I get 1x. 3x, if you recall, this is the same as x added to itself 3 times. So 3x values are the same thing as 6. So if I split them up into their individual parts, the 6 being split up into 3 individual parts becomes 3 pieces of 2. So therefore, by splitting this into its 3 parts, I know that x must equal 2. Why? Well, because 3x was the same as 6, and I can split them into those components. So this must be true if this is true, and this must be true if the original statement we were given is true. So stating our reasons and showing that it's all interconnected, that is logic. That is using logical deduction. So how is math logic? Exactly like this. From the foundation of numbers, it's logical, but at the same time, even problem solving, algebra especially, is specifically deduction.